Hello, everyone. Welcome to Midterm 1, Question 6, Summer 2021 Walkthrough. Okay, so before we actually get into the question, I want to review the circular topology for doubly linked decks or DQs, as one might say. Okay, so you start off with the node, okay? Like this is like the basic building block, and a node has three things. It has a value, well, it has an item, okay? But that's like the value in the node. It has a next and a previous pointer to other nodes, okay? The next points to the next node in the list, and the previous points to the previous node in the list. That's why we call it doubly linked. Why is it circular? Because like literally like loops around. Like if you like wanted to like keep going dot next on like a node, it would keep going on forever. Okay, why? Because we have a special sentinel node. By the way, this is the only node that the entire class has a pointer to. Okay, the sentinel node is special because it's always there. Even if the list is empty, the sentinel node will still be there. And its value or item, we don't care about it because it's like not a real node for the purposes of the like list representation. Okay, sentinel.next points to the first node and sentinel.previous points to the last node. And likewise, the first node.previous points to the sentinel and the last node.next points to the sentinel as well. That makes it circular, right? Because you go from sentinel.next, .next, .next, .next. Oh, that's a sentinel again. Important to note, that's how we can tell if we're at the end of the list, right? If we start off at sentinel.next, which is the first node, and then we keep going across, if we get back at sentinel, then we know that we're at the end of the list. Okay, so the problem is we want to basically, for some int linked list deck, we want to find the node with the smallest value, okay? So just a quick review of the syntax for the class, right? Okay, we have our node, or our sentinel node, which is the only thing we're pointing at. And we have like a private class node. Okay, it's like its value, the next and the previous pointer. Okay, don't worry about the fact that the constructor or anything else is not shown for any of these. It doesn't matter. What you should assume is that everything has been set up correctly. Okay, so we want to find the minimum value or node. Well, but basically the value, right? Okay, so what's the strategy? Okay, so if this were a list, we would just iterate across. We would store like a temporary variable, or we'd store a variable representing the minimum value we found so far, and we would keep going on. And so natural instinct, why not just try to apply this same idea, the same algorithm, as one might say, to linked lists? Okay, so we'll visit every node. We kind of need to, because we need to look at every value, and then we'll compare values, and then we'll try to update some variable. Okay, let's get on to like the skeleton code that we've been provided with. Oh, I need to prepare. Oh, okay, there we go. Okay, so this is what we were given. Okay, I really want to point out something special here. This is a very common paradigm that you will encounter, or at least I hope you encounter when doing linked lists, because it makes them a lot easier to think about and they're very natural. Okay, so you have the method we actually want to implement here, this private node get minimum node, okay? But all it does is it immediately returns something, okay? Now, as a bit of a hint, it returns this like little special helper function, okay? Notice how it takes in a node. That's what separates it from this one, okay? And inside it has like a base case, it has like a line, who knows what that's for, and then it returns something, okay? Right? Okay, like literally it's three components. It has a base case, it does something, and then it returns something. Okay, but this framework's actually really powerful because it's a recursive one. Okay, so like as a hint, maybe okay, this like second step here, it's going to be a recursion. Okay, because that's kind of where the power of this comes from. Okay, because how should you think about these helper methods? You should think about them as they are doing they're doing the function that they need to be doing, but they're doing it at the specific node. Okay, so if I give it a specific node, what it should mean is I want to find the minimum node at this node or after it. Okay, I want you to think about that for a second, because that's kind of like once you realize that, that's kind of like that's like the salt. No, it's not really the salt. I guess It's like the main, I don't know. Okay, if you think about this as like some dinner or something like that, this is like this is the main meal. I don't know. This is like kind of the important stuff. It's like the sauce. It's a secret sauce. Okay. And why do you think of it this way? Because okay, the hint was to apply, and the problem was to apply recursion, and that's kind of like the natural recursive thing to do, right? It's like, you know, pass something into a function and then assume that it does its job correctly, and then rebuild and then take that result and then use it to construct like a new one. Okay, so let's get this started. Okay, so we want to return. Okay, so okay, we're going to delegate it to the helper node or the helper function. Okay, the question is, what do we pass in? Okay, so we like literally only have one node, right? Like we have Sentinel, that's it. So we could pass in Sentinel. But that's actually not our only choice, right? Because we can always go Sentinel.next. This is always well-defined. Remember, it's always well-defined because at worst case, it'll just be Sentinel again if it's an empty list. Okay, so we could pass in Sentinel or Sentinel.next, basically. I mean, we could also go Sentinel.next.next, but that kind of gets like redundant and meaningless, okay? Like our real choices are Sentinel or Sentinel.next. I mean, I guess we could do Sentinel.prev, but okay, like that's maybe hard to think about. Let's just do Sentinel.next. Okay, but we don't know necessarily. We don't know necessarily. So, if you don't know which one to pass in, okay, it might be good to move on and see how the rest of the function turns out. Let's go to the base case. So the base case is, okay, if something, we're going to return null. Okay. Well, okay, in our recursion here, we're probably going to somehow invoke this function to go down the list, right? Right. That's kind of what we stated in our vague strategy, and that's kind of the natural recursive thing to do, is to continue down the list. So probably we want our base case to be, how about like if we like reach the end of the list, we will stop. Okay, like we're going to return null. So how do we know we're at the end of the list? I actually said that earlier in the presentation. Okay, basically, okay, remember it's circular. So okay, there's like a special node that if we get there, we know we've gone through every other node in the list. Okay, and that's the Sentinel node. Okay, so if T is equal to Sentinel, then we know that we have recursed through every single node in the list already. Okay, so if T is Sentinel, we're done. We don't need to do anything. We're just going to return null because Sentinel has no value. Okay, and I really want to point out, this very directly influences our choice here, okay? To return Sentinel or Sentinel.next. Let's see why. If I just pass in Sentinel, then immediately in get minimum node, the first T is Sentinel. And Sentinel is equal to Sentinel, so you return null. That's not very good, okay? Because we actually want to iterate across the rest of the list. So, okay, let's return .next. And in hindsight, maybe that makes sense because Sentinel.next is the first node that we're actually going to be looking at. So maybe it's kind of a waste of time anyways to look at Sentinel because we just want to skip it. Okay, the second step, recursion. Okay, like that's basically the only thing we can do. So we know we're going to take in some node. Okay, let's just call it S. And it's going to get the minimum node. Okay, and okay, what do we call it on? Well, T.next is kind of the logical choice because, again, we kind of want to iterate across this entire list. Okay. Now it's time for the recursive case. And here's where I want to point out, right? This is supposed to be getting us the minimum node. We actually haven't really thought about that too much. Like we were basically just like, we want to go across every node. And all we did, this is the power of the framework. It's kind of general, right? Because we basically just wrote something that'll iterate across every node and then returns something, okay? Based on like some calculations it makes or something. That's very powerful. And this is why I really want to emphasize that this framework is so good to know. It's because like, like we haven't thought about the fact that we're trying to get the minimum node yet. Okay, this is what we have to think about here. Okay, and so, okay. So this is where we want to take our recursive leap of faith, as one might say, okay? We want to assume that get minimum node worked on T.next. What does work mean? It means that node S is the minimum node after T, okay? And so remember, what is get minimum node on node T supposed to do? It's supposed to return the minimum node at or after T. So if we have the minimum node after T, we just need to compare the node that to the node at T, okay? Because like we know it's the minimum after T, so we just need to make sure that like it's smaller. It really is smaller than t, or otherwise we got to just return t. Okay, so how do we do a comparison? Well, we're comparing their values, right? Oh, I just realized that in the slides it was item. Okay, it's kind of the same thing. We'll just change this to item. Okay. Okie dokie. Okay, so what do we want to do? Okay, so like let's just say if t dot value is greater than s dot value, then let's just return s. Okay. Otherwise, let's return t. Okay. Why? Because t dot value. Okay, if t dot value is greater than s dot value, that means s really is the minimum node, and we should return it. But if it's not, that means t is actually the minimum node. We should return that. And so there we go. This is actually the entire function done because, right, we implemented something that's going to iterate across every node, and then, it's going to return some stuff. Well, it'll return, like, at each step, it'll return, like, it'll determine, okay, is this the minimum or is this the minimum? And it'll return something. Okay, and we're done. Psych. I really hope no one stopped watching the video, like, after I said we're done, okay? Because we're not done, okay? There's actually a really important thing. Okay, this code totally doesn't work. It's going to break the moment you try it. Why? Okay, notice we return null here. Okay, so think about it for a second. Think about it. Okay, let's say that t is the last node in the list. Okay, meaning t dot next is sentinel. Okay, so you try to get node s, get minimum node on t dot next. T dot next is sentinel, meaning in the recursive call, t is sentinel. Okay, in this call, in this new call. Okay, meaning you return null. So s is null. Okay, and then you're like, okay, la-di-da, is t dot value greater than null dot value? Null pointer exception. Oh no, right? That'll break. And because you're always going to finish the list at some point, assuming it isn't some weird infinite thing, you're screwed. Okay, like you're literally, it's just not going to work in any case. Okay, so this is kind of a disaster. This actually doesn't work at all. Okay, so we need some way of basically like, if s is null, what are we going to do? Okay. And this is where we've got to remember the most beautiful thing, which is that if statement short circuit. What does that mean? It means, okay, like, oh, did I? Oh, no, I didn't. Okay, meaning if I have some condition before that, and I go like and, okay, like, if this condition fails, right? In order for, okay, remember, we put an and thing down, two ampersands. Both these conditions have to be true in order for this if statement to be true overall and to trigger. Okay. Meaning, if you go and check this condition and it turns out to be false, you don't need to bother checking this condition, okay? And Java doesn't, and pretty much no programming language does, right? It's just a waste of time. You can just go on and say, okay, we know this whole thing's false. Okay, so we can take advantage of that. If we have some condition here that's like, okay, like if s is null, or if s is like whatever, if s is null, then it evaluates the false. It's not going to check this, so it's not going to raise a null pointer exception. I'll just go and return t, which is what we expect. Okay. And the condition is literally as straightforward as saying, okay, as long as s is not equal to null. Yeah. So yeah. Okay. Like we got to make sure. Okay, if s is null, s is not null. We got to make sure s is not null, and t dot value is greater than s dot value. Okay, return s. Otherwise, return t. It's as simple as that. Okay, because we can check this. If s is null, we want to return t because we don't want to keep returning null, so we to return t. Okay, but if it's not null, but t is actually less than it, this is false, and so we return t anyways. But otherwise, we return that s. Okay, and that's exactly what we expect. And so this is actually exactly the solution. Okay. And I really, really urge all of you to make sure you understand this example thoroughly, because this is like I said, this is a really good paradigm or strategy or whatever you want to call it for approaching these kinds of problems. And I really would recommend all of you to really keep this in mind when you're doing stuff with linked lists. So yeah, so with that said, I guess thank y'all for watching. And I hope to maybe see you guys for part B. Maybe. Okay, whatever. Have fun, everyone. Bye-bye.